As we have learned, the convolution properties such as commutative property, associative property, distributive properties, and so on. Now, we need to learn what is the impulse response. So, impulse response, as the name says, for a system, let's consider a system. For a system, if a unit impulse is the input, so we know unit impulse signal, which is represented by del of n. When del of n is applied to our system, which is having its transfer function as h of n, or it could be h of t. Let's learn it with respect to one domain, discrete or continuous. So if h of n is my system transfer function and del of n is the input to my system, then whatever the response I get, this response I represent it as y of n. And this response y of n is nothing but h of n in convolution with del of n, or vice versa, del of n convolution with h of n, resulting into h of n, which is referred as the impulse response of the system. I hope you'll get what is meant by the impulse response of the system. Impulse response is the response of the system to an applied unit impulse signal. So to which we write the output as the same, the transfer function, that is h of n only. Now we need to learn some properties with respect to this impulse response. So for that, let's consider x of n and h of n signal, and then we can correlate it to the impulse signals. And we know that x of n convolution h of n is equal to h of n convolution x of n, and the same can be expanded. We'll get these equations. Now, to study the causalness of the system, this causalness of the system is defined as the system is said to be causal if the output of the system depends on present or past values of the input signal. I mean, the output of the system may depend on just present, or may just depend on past, or even it may depend on present as well as past values of the inputs. If the output of the system starts depending on the future values of our input signal, if it starts depending on the future values, just like x of n plus 1, if it starts depending on the future values of the system, then we can't say that it is a causal system. So to be a causal system, our x of n, our output should not depend on the future values. So let's learn regarding this. So we'll consider the second equation, which fits better for understanding. So for this, we have considered this h of k, x of n minus k signal. Now for that, let's consider x of n signal. Let our x of n signal be this way. Let's say its span is from minus infinity to plus infinity. Now let's have the glance that the signal x of n is having its samples at 0, 1, 2, 3 and so on. Let's say it has on the positive side of our axis. Then our y of n, the output of the system. The output of the system as per the second equation, because this thing will not be revealed by the first equation. So let's learn it with respect to the second. So we'll consider this equation. In this equation, we have x of n minus k as per the definition, and we know that the convolution is commutative. When this x of n minus k is the input term, it is the shifted version of the input term, we know. So this x of n minus k will be positive. Now we'll talk about this n minus k. This x of n minus k is, when k is a 0, it becomes x of n. When k is 1, it is x of n minus 1. When k is 2, it is x of n minus 2, and so on. I mean, if the values of our x of n signal are lying on the positive side of our axis or right hand side of our axis, then we start getting the values like if the value is present at 0, then it is x of n, means the present value of the output, the present value of the input. The output depends on the present value of the input. And if the values, if the samples are present at the right side, then we start getting the values like x of n minus whatever it is. Then the thing is satisfied for the causalness, like the output of the system depends on the present and or past values of the input signal. Now, if we consider the k as, if the value of this k becomes as -1, -2, -3 and so on. I mean, if this x of n starts having, let's say, the sample, whatever may be its value, if it starts having the samples at -1, -2 and so on, then we start getting the terms like x of n minus, it is x of n minus, now -1, it would be x of n plus 1. If it is at -2, then x of n plus 2. Then we start getting the positive, like our present output of the system, the output of the system depends on the future values of the input signal. So at least if it depends on one of them, I mean if x of n is having one sample on the left hand side of its axis, maybe at -1, -2 or at any value of the minus side, then certainly will get x of n plus a value, and our signal starts becoming like non-causal. So what is the condition for causality? The condition for causality is our signal should have only the right side part, maybe it is from 0. And if it is having the signals, if the samples are lying or if the signal is existing on the left side of its, I mean from -infinity to -1 or maybe on the left side of 0, if any of the sample or if the signal is having its value as non-zero on the left side, then our system becomes non-causal. So we are establishing the condition for causalness of the system. The condition for the causalness of the system is like this. The condition for causalness of the system is this way. Our h of n is equal to 0 for n less than 0. I mean, if any of the sample, in case of discrete signals, none of the samples are there, or if the samples are there, they are of 0 value. That is the representation. And the same with continuous signals. If our h of t is 0 for t less than, means even though if it is a continuous signal, on this side, if the signal is lying in this way, if the signal is lying only on the positive side, maybe in whatever the extent, then the system is said to be causal. So the condition for causalness is this one. On the left side, there should not be any value of our signals. I hope the causalness is clear. We'll go for the next point, that is memoryless. A system is said to be memoryless. We know that the definition of the memory is like the output of the system, it may be a continuous or discrete system, if the output of the system depends on present or past values of the, if it starts depending on the past or future values of the system, then it is said to be with memory, means x of n plus 1, or it could be x of n in whatever the way. So x of n plus 1 or x of n, whatever it could be. So x of n plus values, whatever these ones would be, or if the system is like x of n minus something, x of n minus 1, x of n minus 2 and so on. So the system is said to be with memory if the output of the system depends on the future or past values of the input. If it is just depending on the present value of the input, then it is said to be memoryless. So to be memoryless, the condition is what? It should not depend on either x of n plus values or x of n minus values. It should just depend on r x of n. If it is just depending on x of n, then the system set is said to be memoryless. Then let's have a glance on this equation again. In this equation, this system will become memoryless only for what value of k? It depends. If the k's are like 0, 1, 2 and so on, we start getting this x of n minus 1, x of n minus 2, x of n minus 3 and so on. We start getting this up till it may extend to infinity. And if the values of our k's are minus 1, minus 2, we start getting this x of n plus 1, x of n plus 2 and so on. We start getting these values. So as long as these values are present, we can't say our system is memoryless. A system is said to be memoryless if the output of the system depends on only the present value of our input. So this is possible only when k takes 0 value. This is possible when k is equal to 0. Otherwise, for other values of k, it is impossible. So the condition for memoryless is this one. Our system will be having the condition as h of n is equal to 0 for n not equal to 0, means the signal should be there, present only at the 0th instance, and it should not be there anywhere else. So if it is present at only the 0th instant, and if it is not having its values for other values on the left side or even on the right side. So if the values are not present at other instances than 0, then the signal or the system is said to be memoryless. So h of n is equal to 0 for n not equal to 0, or h of t is equal to 0 for t not equal to 0, means for other values other than 0, for all values other than 0, our system will be having 0 values. So if this is the condition, then our system is said to be memoryless. I hope we are getting this. So h of n is equal to 0 for n not equal to 0. Then the last one is regarding the stability of the system. As we know, the system is said to be stable if the bounded input produces the bounded output. So as unit impulse response is there, certainly we'll be applying the bounded input and we'll be checking for the bounded output. So for this, the conditions are as here. The conditions are, so summation of, if after solving the summation k from minus infinity to plus infinity, the magnitude of h of k, if the answer works out to be less than infinity, then we say the system as stable. It would be stable. If we get the answer which is like infinity, then we say it is not stable. The same is with respect to continuous signals. When we solve this integration from minus infinity to plus infinity, h of tau d tau, of course, h of tau d tau, if this works out to be less than infinity, then certainly this would be a stable system. Otherwise, it is unstable. And these would be more clear when we go for solving the examples. So let's see a problem and understand these things in a more detailed way. And in case of this, we are learning with respect to x of n, but as we are learning the impulse response, our input is del of n. So we'll be given with only h of n, and h of n will be the output of the system. So let's consider this problem. The impulse response h of n of the system is given by half raised to n u of n. And for this system, we have to check whether it is causal or non-causal, whether it is memoryless or not, whether it is stable or unstable. So to check this, as we already know that the conditions for the causalness. So let's draw the signal. H of n is equal to half raised to n u of n. We know half raised to n is multiplied with u of n. So our decaying exponential is getting multiplied with the positive sided step signal. So we'll be getting this kind of a signal. And for this, let's check what about causalness. So for a system to be causal, the condition is, as we saw, the condition is this one. H of n is equal to 0 for n less than 0. I mean, the signal should not be there on the left side. It should be there on the right side. So from there, it's clear that our signal, this h of n, is there only on the right hand side and it is not there on the left hand side. So straight away, so we can write it with respect to k or with respect to n. H of n or h of k is equal to 0 for n or k less than 0. So this condition h of n is equal to 0 for n less than 0 is satisfied. So we can say it is causal. Then let's check about the memoryless. A system is said to be memoryless if it is satisfying this condition. Why these conditions have been put, I hope you know. So as discussed just earlier, so h of n is equal to 0 for n not equal to 0. So h of n is equal to 0 for n not equal to 0 means the signal should have its value only at the 0th instance and it should not have the values on rest of the instances, at rest of the instances. So, but as we can see, it is having the samples on the right hand side. So we get the terms like x of n minus whatever, the x of n minus 1, x of n minus 2 and so on. Means it is having the memory because it is having x of n plus x of n minus 1, x of n minus 2 and so on. So this condition is failed. So our system is not memoryless. So here the system is causal or not regarding the causalness. Now here our system will become a causal. Now it is not causal, we have written. So it is a causal system because it satisfies. But here the memoryless, it is not memoryless. It is having the memory as the signal is not existing only at the 0th instance. Then the next point is regarding the solution of the problem, like stability. So let's check about the stability. To check the stability, we know that we should satisfy this condition. That is, our summation k from minus infinity to plus infinity, magnitude of h of k, when we solve this one, it should come as less than infinity. So let's solve that way. So when we go for solving this, so this is the condition. After checking this, we'll arrive at the conclusion. So summation k from 0 to infinity. Now we'll substitute. Now here the signal given is h of n, but we do indexing because the convolution process is there, even though it may be with respect to the step unit impulse signal. So let's write that equation which is h of k. So to get h of k from h of n, we do indexing, just the same signal is redrawn. and indexing is done. Now here it is the k variable, not the n. So h of k signal, and this h of k signal, this h of n becomes h of k, which is nothing but 1 by 2 raised to k, u of k it would be. So when this becomes 1 by 2 raised to k, 1 by 2 raised to k, u of k, it is u of k. As we know, this u of k means right hand side. So the summation was from minus infinity to plus infinity, but as we are having it only on the right side, so let's make it as from 0 to infinity, it is half raised to k. And from the knowledge that we have the formula summation if some alpha raised to k is there, and that k is from minus infinity to plus infinity, or if that k is from 0 to infinity, it is alpha raised to k. This is given by 1 minus alpha. So from this we can write, and this is valid if the value of this alpha is less than 1, and certainly this 1 by 2 is less than 1. So we can use this formula, gives the answer as 1 by 1 minus 1 by 2. And when we solve this one, it is half, and denominator of denominator is 2, so it is 2. So we get the answer as 2, which is certainly less than infinity. So the system is stable. So we arrive at the conclusion that the given system is stable. Now let me repeat the things if any confusion is there. The signal, whatever is given for the impulse response signal, whatever is given, it is causal because it satisfies h of n is equal to 0 and less than 0 signal, because it is not having anything on the left side. Memoryless. To be memoryless, h of n is equal to 0 for n not equal to 0 is the condition. Means it should be present only at the 0th instance. But it is not so with our signal. Our signal is having the samples on the right side, so it fails. So the system is not memoryless. And regarding stability, when we do indexing and take up this equation and solve, and now magnitude sign, because the thing is totally positive, so we can write it as just half raised to k. So by this equation, which will be given as 2, so the system is stable. Now we can solve some more problems of this kind in the next one. I hope you are getting what are these properties.